Hello, everyone. Let's go into another 450 example. This one will be on the ideal diesel cycle under the cold air standard assumption. So the cold air standard is useful, but there's still, and very simple, but there's still some very important uh, details which often get skipped in textbooks, but I think they show there's a useful time to remind us of the general strategy, the general approach using the first law. Okay, so the standard diesel cycle, oftentimes you start at 1 atmosphere, 1 ATM on this PV diagram. So starting here at the biggest volume, bottom dead center, you'd go into this compression stroke all the way up to the highest pressure. For this would be 1 and 2 here. And what the diesel cycle does in the ideal case is ideal simplified cold air standard. You have this work in isentropic and instead of having an internal combustion engine where you increase the temperature, you have Q in as like a thermal heat reservoir at high temperature. In that, instead of the temperature increases, but the pressure stays constant because you are allowing this cylinder to expand to some extent. So as the energy is coming in, the temperature increases, but the pressure does not because you're allowing the pressure stays constant due to this increase in volume to accommodate for that energy. Then you complete another workout stroke. So this is also some movement of boundaries. So this can be considered work out here from 2 to 3, but oftentimes books gloss over that and they do a couple things that we'll talk about next. So that's a power stroke, part of the power stroke, but then the power stroke that most books consider as well, or they just skip over, is from work out from 3 to 4. So this would be state 4. It's an isentropic as well, in the ideal case. So that would be the net work would be this workout during the heat in combustion and type stage. Then you have this other isentropic expansion from high temperature to lower temperature, the highest temperature to the lowest temperature. Oops. Then to get back to your original state in the ideal case, you do not exhaust the spent combustion products. You just simply have this heat exchange exhaust-like stage from 4 to 1. And so this is the cold air standard. It's the same pocket of air undergoing 4 stages, 4 states, and it begins at state 1, ends at state 1. Same pocket of air. Even though it's simplified, and we're going to simplify it even more with the cold air standard, it's still going to give us some nice physical insights. Okay, so in this problem, let's say we are given that the compression ratio is 18 and the cutoff ratio is 2. And the bottom dead center, which is V1, is 0.8 liters. So this is the maximum volume seen in the cylinder. And then the volume doesn't go to 0 when it gets compressed, but it's the minimum when it gets compressed. But this is the maximum before compression. Okay, so the questions are, what are the system states 1 through 4? Okay, we'll find that. What is thermal, diesel, cold? What is the thermal efficiency of this diesel cycle under cold air standard assumptions? Well, spoiler alert, as we spoke about in class in the book, hopefully you've seen, if you do this analysis, the classical result is that it only depends on the compression ratio, which is R, and the if we're talking about the air standard, this K is 1.4. Spoiler alert, you can use that to find this, okay, fine. But I'm going to show you the analysis to find each of these states on this process as well. And this also equals, by default, the first fundamental definition of all heat engines is the work net out over the QH. So in this simplified diesel cycle, the ideal case, we're going to replace it with this heat transfer in and some work net out. And the interesting thing about this cycle is that during this heat transfer stage in, there's also some work out there. There's a work out here. So there's 2 workouts, 1 work in. We'll talk about that as we go along. Okay, so to start this analysis, we're going to go ahead right away and use the compression ratio. So V2 would be the volume at state 2. We're just going to simply use the compression ratio there. We're given the maximum volume of 0.8 milliliters or 0.8 liters. Convert to milliliters, you'll get this. So that means the top dead center is that, just by using the compression ratio. Then just by using the cutoff ratio, its cutoff ratio connects to V2, which we just found. So this would be and this is a rounding error. I said 44 here, but this 49 comes in because of the rounding that I didn't show previously. So that's V3. Okay, so those are easy. Those are just from the cutoff ratio and compression ratio. Then under the cold air standard, we can use these isentropic compression CP CV constant relationship, which is that T2 equals T1 times this, which is basically related to the compression ratio. So that would be assuming, let's assume this is 300 Kelvin, like in San Diego. T1 is the ambient condition. So that would be 300 Kelvin times 18 to the 0.4. So T2 equals 953 Kelvin. Okay, so state 2 is pretty much known. Well, no, we'll find the pressure, P2. We need the pressure now. Similarly, you can use these isentropic relations to get this pressure ratios. Again, assuming we're in San Diego, 1 atmosphere is our starting condition. super hot, high pressure. This diesel engines, the compression ratio is 18. So when you do that long stroke of them from the maximum volume, bottom dead center to top dead center, at the end, the pressure is going to be almost 60 times higher pressure than where you started, which is typical diesel, what happens in a diesel engine. If you try to do this to gasoline, it'll knock and go crazy. Okay, so that's state 2. We found the volume of state 2, temperature of state 2, pressure of state 2. So volume of state 3 we found from cutoff ratio. Now we have to find another way to find the pressure and temperature. So from 2 to 3, it's an isobaric heat in with expansion. What that means is the pressure stays the same, but the volume increases and the temperature increases with the heat in. So for we'll just use the ideal gas law. And this old school chemistry thing, P2 V2 over T2 equals the ideal gas constant times the moles, but that doesn't change. So that has to link you to P3 V3 over T3 because this stays constant. The universal gas constant and the moles. So that's why you can say this as we did in high school chemistry, I hope. Okay, so that simplifies with the fact that pressure stays constant. So P2 equals P3 equals 57 atmospheres. So that's known. Now we can relate T3 to T2. Oops. Which we already found from the cutoff ratio. We know V3, and that cutoff ratio is here literally. So that would be very hot. So this should be the hottest temperature because it's after the combustion. So T3, 1905. We already found V3 and V2, P2 equals P3. So that's state 3. Okay. So the isentropic expansion for the cold air standard, again, we can do the same relationships. We end at T4 after expansion from T3. So this V3 is depends on the cutoff ratio. V4 depends on the compression, but we already found those, so we can just plug those in. Because V4 equals V1 in an ideal case. So that would give us T4. Okay. Similarly, so I just skipped this. This would be the same, 89 over 800. So that is V4. Yeah, V4 equals 800 mils. That's done. So we now know state 4, and we know all the states now. State 1, I guess we can explicitly say this. State 1 T1 equals 300 Kelvin from San Diego. P1 equals 1 ATM. B1 is given 800 mils. So that was given, state 1. Then we went from there based on the compression ratio, the cutoff ratio, these cold air isentropic relations, and this isobaric ideal gas relation. So we know all the states. So that's good. And okay, we can plug in the compression ratio and the cutoff ratio to get the thermal efficiency, which is we can already do. We have all we need to find thermal efficiency. But let's talk about how it's basically deriving the thermal efficiency equation. But besides that, it's interesting that we can apply our first law analysis. We have always been applying the whole 2 semesters now. But the book often skips these steps, which I think are important, because it's another example of how you need a lot of practice to get familiar with this first law and all the different situations that can be applied. And I think they're cool because we're talking about an Otto cycle and diesel cycle here. This diesel cycle is the main way we're getting transport of big trucks, big boats, big machinery. This is the theoretical limits of that we're talking about here of this stuff. So pretty still very important stuff. Okay, so let's apply the first law to each of these stages and go eventually to the thermal efficiency. So from the first law, from 1 to 2, first thing you ask, okay, what system am I talking about? Well, this is a closed system. It's a cylinder. We're modeling as a pocket of air, and just getting, there's different stages in the simplified model of the diesel cycle. No internal combustion engine. It's just a pocket of air getting heated and such, as we spoke about. So this is a closed system, and it's not the internal combustion engine. So there's no reactions, no chemical reactions. So as I spoke about a few times, that means use delta U for the energy levels of the system. Okay, so when we do that, it would be delta U. We're going to neglect kinetic energy change, neglect potential energy change as usual. And that would be then this change in internal energy U is balanced by this net heat in and this net work out. Okay. So, or you can also say delta U equals Q minus W. That's what these symbols mean. And for the cold air assumption, cold air, delta U equals mCV delta T. Okay. And in the first law, first process going from 1 to 2, we're going to ignore the heat transfer. It's going to be an isentropic compression. But for cold air, which means delta S equals 0 and CP CV constant, K equals 1.4. What you may remember is that the work equals the integral of PdV. In solving for this case, this would this special equation P2V2 minus P1V1 over 1 minus K. And in this case, because delta V is, it's less than 0. That means it's work in. That means that the number you get here should be less than 0. So K equals 1.4. That's why we got this simple relationship. Okay. And here you need the mass. The mass cancels out here. So let's find the mass. So using the ideal gas equation, the pressure times the big V, the meters cubed, equals the mass of air times the ideal gas constant for air times the temperature. So that means the mass equals P1 V1. Let's just pick one state. Okay. So it's often a units exercise to convert. This is energy, at the PV is energy, R is related to energy. So let's convert atmospheres to kilopascals. This is kilonewtons per meter squared. That's what kilopascals are. And let's convert V1 to meters cubed. And the units for that are related to the fact that 1 kilopascal times 1 meter cubed equals 1 kilojoule. And you should remember for air, under the cold air standard, this equals 0.287 kilojoules per kilogram of air per Kelvin. Okay, so skipping all the calculations directly, I just showed you the useful units conversions. You should get 9.4 times 10 to the negative 4 kilojoules in this particular cylinder. So again, the book skips all this because there's a much faster way to get it, which at the end results in this equation only as a function of compression ratio and cutoff ratio. But the way you get there is the standard steps we've been taking from all the cycles we've talked about so far. We just apply the first law of thermodynamics for each stage. Okay, so now let's go to state the 2 to 3 process. So this will be the first law from 2 to 3, which is an isobaric expansion with heat in. This is where the book skips a few steps. Again, this is a closed system, no reaction. So the first law would be delta U equals Q minus W. And we can also just break this up into Q in minus Q out. Okay, this is only heat in, and because delta V is greater than 0, this just means it's work out. Okay. And under the cold air, you would get, okay, that's not, so that would mean, okay, but then when you were for all at the beginning of even last semester, we said, how is work related to the integral of PdV? In this case, for isobaric, it's P delta V, isobaric expansion. And that would be, P2 equals V3 times V3 minus V2. So this would be delta U from 2 to 3 equals Qn from 2 to 3 minus, so this is work out, let's keep the minus here, work out from 2 to 3, and if this is positive here, then the work out would be minus P3, whatever P or 2 or 3. Okay. So that was the first law, what the first law would be. But then the book somehow, just quickly plugs in without explaining much that they just skip a few steps. Here's another step, is that you can relate enthalpy to internal energy for all cases, as long as you know the pressure volume term and the internal energy U term, that's what enthalpy is. And we use that when there's flowing system, that PV term accounts for the flow. When there's a reacting system, it keeps to account these PV effects due to reaction. That's why we use delta H in many cases. This is a third case where just simply it's useful to combine these pressure and volume terms. So in this case, it will be Qn from 2 to 3 equals delta U from 2 to 3 plus P2 so that would be U3 minus U2 plus P2 V3 minus P2 V2. So that would mean that's where it comes from. That's why quickly the book just says, oh yeah, obviously Qn can just be expressed in terms of H3 minus H2. It's not too difficult, but it'll be nice if they would remind us of why they did that. So you can express it. There is a work term here because a boundary moves, so it is work, but it is also a PV term. Sometimes this PV term is there without work. Sometimes this PV term is there with work. Either way, mathematically, that's what the enthalpy term captures. So that's what would be in this diesel cycle, constant pressure heat in with this volume change can be expressed in terms of this enthalpy change, even though it's a closed system, no reactions. In this case, it's because the boundary moves. That's why the enthalpy comes into play, and the book just skips that many times. And for cold air, this would be just simply at 300. And that's because the enthalpy change is related to Cp, not Qn. It's enthalpy. It's the enthalpy coefficient. Cp is the enthalpy capacity. Okay, let's go to first law for the next stage, 3 to 4, isentropic expansion. So this would be delta U equals negative W, where for isentropic expansion, it's B4V4 minus P3V3 over 1 minus K. That's the work term there. So where this would be an expansion, delta V is greater than 0. So it's work out. So that means work is this number you put is less than 0. Yeah. Okay. But it's also for cold air, delta U equals CV delta T from 3 to 4, and so forth. Okay, moving on to the next stage. First law for 4 to 1. Under the cold air standard. You get that. Okay, and as a reminder, you can also do the first law over all the states over the whole cycle. That would mean delta U cycle equals U1 minus U1 equals 0 equals Q in minus Q out for the cycle minus work out minus work in for the cycle. So that's what the book does right away. They say because it's a cycle, the state of the energy level of your working fluid does not change, but it does not change. So that means that the Q in or the Q out for the whole over every stage has to equal work out minus work in for the cycle. Okay, and if we go through each cycle, through each stage all the way over here, the interesting thing is for this cycle is going through the heat energy transfers from 1 to 2, that's work in, but going from 2 to 3, there's both heat and work. So that one has both. And then going from 3 to 4, it's only work, and 4 to 1, it's only heat. So the net work has a few different terms. So Q in would be Q in would be only from 2 to 3. Q out would be only from 4 to 1. But the work out, there's a work out from the combustion from 2 to 3, the boundary moves. So it's getting heat and it's expanding. So there's some work out. Then there's another work out from 3 to 4. So those are two different work out terms that should be accounted for. The book skipped this because they just go to this, which is easier, but they don't explain what they're doing. These are both work out. And then work in from the first compression stage. The book just simply goes to these. Why? Because these are just simply under the cold air standard, MCV T3 minus T2 minus MCV T1 minus T4 or whatever to make it positive. So it's, oh yeah. So that was my point. When you, is that it's nice that it still works. But we know why the book does that, because it can just all right away, because the whole point is to get this classical expression, and the thermal efficiency for a heat engine is always the work net out over the QH stage. And by the law of the cycle, you can relate the work to the heat. So you can say 1 minus Q loss or QH. Then you can just say this is just, that's why they do it. You can just skip all that. And then you can then again eventually get a function of R and RC under the cold air standard. But you should get the same answer if you were to go back to this work terms to say this should be work out from 2 to 3 plus the work out from 3 to 4 minus the work in from 1 to 2 over the Q in from 2 to 3. So the 2 to 3, there's both a work term and a heat term in there. And we should be able to find, we have found all the states and we have the models. So this would be, in this case, P3, V3. Yeah, that's the isobaric case. Plus, this is another expansion. So P4, V4 minus P3, V3 over 1 minus K minus, let's switch the signs around. This should stay consistent. This should be just the absolute value. Let's just put absolute values in. Absolute value, absolute value, absolute value. There should be absolute value of P2, V2 minus P1, V1. This is going to be a negative value because the pressure, the volume's less at the end. Oops, what did I do there? Absolute value over CV under the cold air standard mass. Oops. You should get the same thing. So that's just showing it's just a network. Okay, so at the end, either through just plugging it in from the compression ratios or by doing all this other analysis, this is what you should get. Okay, so at the we found all the states. That was useful to see. For the cold air, you don't have to use the relative pressure. You just use these ratios, cold air ratios, to connect the states from one to another. And then of course you use the compression ratio and the cutoff ratio. Those are very useful as well. And you can find the thermal efficiency right away. This is all derived from the same analysis. It's just simplified into this expression here under the cold air standard. But where that expression comes from is all of this analysis here, and not all of it because the book often skips it and goes straight to this simplification to go to here, and then it plugs in everything and does some algebra to get this function of compression ratio and thing. But it should give you the same answer to remember that there's two work outs here and this compression step in, and either way you should get 0.48 in this particular starting volume and starting temperatures and pressures. Okay, so that's good. Thank you, and email me with any questions, please.